It's very big.
No, he's very good.
It's good. So, ready?
Actually, we can look at some of the
We'll start now. So, welcome to the Symbolic-Numeric Computing Seminar. That's the first seminar. Session of the seminar. So, welcome Professor Robert Lewis from Fordham University. He'll be talking on symbolic-numeric solutions of polynomial systems using Dixon resultants on image analysis problems.
Thank you very much. Thanks for inviting me. Okay, well, you probably read the intro there. So this is about symbolic numeric solutions of systems of polynomial equations, focusing on problems that come from some kind of geometry or image analysis. Okay, so let's say I gotta scroll, right?
First,
Does this work? Okay. So there are various projects I'm going to talk about, three mainly. These are my various co-authors. Evangelos Koutsias on the first project. He's now at Stony Brook. Nazar Khan is back in Pakistan. Bela Palanks is in Bulgaria. And Joseph Awangi is now in Australia. So we got a worldwide bunch here. Okay, so polynomial systems. What's a polynomial system? I found over the years it means different things to different people. Basically, everyone agrees that you have a bunch of polynomials, multivariate, of course. You're going to see each to 0, and we're trying to find common roots. So what's the ground ring K? So we have a ground ring K, I'll talk about it in a minute. We have variables, x1 through xn, and almost always we have parameters, say a1 through am. So what's really going on is you have the polynomial ring K of a1 through am, so that's kind of your base. If you wish, you could think of the field of rational functions, K of a1 through am. Then you have these n polynomial variables. The applications I do, K is primarily Z or Q if you wish, often Z mod PZ for reasonably large primes. 40,000 up to about 2 to the 31. Usually use those as a technique, as an artifice. I'm not interested in the field of two elements. I'm not talking about cryptology or cryptography. That's a different world, has a different flavor to it. And I'm not interested in solutions which are entirely numerical. I'm interested in symbolic solutions. At least to the point where I have an equation in one variable and I can turn it over to some numerical solver, at which point I lose interest in it. So I'm interested in symbolic solutions of polynomial systems over exact ground fields.
press left or right.
Press the which?
You can press right or you can press page down.
Oh, okay. So typically I have n equations in these n variables, some parameters. Usually the system is neither over nor under determined. Now it's possible to deal with those, that's an extra complication. Usually I have a zero dimensional solution. There's special symmetry or something. Okay, what does solve the system mean? Right. I mean I've eliminated all but one of the variables. I'm left with one equation and one variable and the parameters. That's usually good enough for me. If desired, numerical values for the parameters could be substituted and then you can do a numerical computation. So how do you do this kind of thing? There are commands, I'm sure you've tried various computer algebra systems. There are commands for triangularizing, there's Grosvenor bases, there's resultants. I'm most interested in resultants. So So if you have like, I don't know, 5 variables, you get the resultant in one of them. You could probably get the resultant in all 5. The nice thing is you can do that in parallel, different machines. You can run that in parallel. So the method I found to be very, very powerful is Bézout-Dixon. So there are a couple more names ought to be mentioned here. Bézout, back around 1760, he had the first basic idea of he had only 2 variables, 2 equations. But there's this neat idea where you form a certain determinant in a certain clever way. So that idea goes back to Bézout. Dixon, 1908, generalized it to 3 or more equations. And the subject kind of died out for a long time. Nobody seemed to be interested in it for a long time. In 1994, Kapoor, Saxena, and Yang revised this method by proving a certain very interesting and powerful result that makes it doable. I think I have time. I should mention that. So I'll probably mention this later, but what's going on with this method is you end up with a matrix. You go through a couple stages and you get this matrix. So the matrix contains the parameters. Now, it doesn't have to be a square matrix. If you go back to what Bézout and Dixon did, Dixon said it's going to be a square matrix, just take its determinant, and that determinant is the resultant. Now, that's only true if you have a completely abstract system. In other words, you have so many parameters that it's totally general. So if you apply this method to real systems of polynomials, you often get something which is not a square matrix. So then you say, what am I supposed to do? How do I take the determinant? It's not a square matrix. You know, duh. Well, the Kapoor, Saxena, and Yang were the first people, at least I know of, who said, all you have to do is find any maximal minor. Extract any maximal minor, and the resultant is a factor of that determinant. That's a very powerful thing. It gives you lots and lots of choices, lots of things you can do. The resultant is a factor of any of the maximal minors. That's something I exploit all the time in my software. Okay. Now, so they published this paper in '94, and they had kind of a, what you want to prove this, of course. And the proof they gave was only valid for a kind of funny special case. Nonetheless, everybody who tried it, soon realized it always works. It works not just for that funny special case. So in 2000, Bouza, El-Kadi, and Moraine published a theorem that showed why it, quote, always works, unquote. Yeah, not always. Really, they showed why this works. Is a good method. Yeah, that paper, by the way, is pretty powerful. I can't understand that paper. That's beyond me. But that's powerful stuff. Everything else up to this point is no more than like junior level undergraduate. There's really nothing deep about this. But that's a paper that I consider deep. Okay, so anyway, the idea is we're going to compute the resultant. Okay, now, then I came along. EDF means early detection of factors. So what's going on here is, okay, choose any maximal minor. Now the resultant is a factor of its determinant. Now, I don't know if you've trying to compute the determinant of a multivariate system. And this is often, goodness, let's just say 20 by 20. It's often bigger than that. I don't know if you've tried, this can be very challenging. The determinant can be gigantic. Now, the neat thing is, we don't necessarily have to compute the entire determinant. All we want is the resultant. The resultant is a factor of it. And in real life, actual problems that people actually care about, it's a relatively small factor. Most of the determinant is junk that you don't care about. Furthermore, often the resultant appears as, like it cubed or something. It's part of this determinant. So all I want is the result. Okay, so I figured out this method by which I can detect the factors early. So the output of this algorithm is a list of polynomials whose product is the determinant. But I don't ever compute the determinant. I have factors. interesting problems tend to have many factors. Right, if you go home and make up some random bunch of polynomials, it will not satisfy this. It won't have lots of factors. And then this method won't do you any good. So like I said, there's no guarantee this will work better than a standard determinant method. However, it certainly has done so. Okay, Grumner bases. I assume everybody's heard of Grumner bases. They have lots of applications, a marvelous idea, among which is solving systems of polynomial equations. Now there's a key difference between resultants and Grumner bases. The resultant of a system is a single polynomial in one variable and the parameters. A Grumner basis used in this way gives you a lot more than that. Typically you end up with a polynomial, which really is sort of the resultant, has one variable and the parameters. Then you get a second polynomial with two of the variables, then another one with three of the variables, and so forth. That's a lot of stuff. That's a lot to ask for. Often the single resultant is sufficient. Right, so that's a huge advantage. Now, I've been doing this for more than 15 years, and I've noticed again and again that when engineers, scientists, and most mathematicians want a solution to a polynomial system, they have in mind a symbolic solution. That's what they really like. So many people, and again, we've seen this again and again, they try Grumner bases, usually either in Maple, Magma, or Mathematica. Or sometimes singular, right? So usually they will try it. Many, many times, the program crashes, the user finally gives up after many hours. This is what happens so often. Okay. These systems would almost always be far easier with Dixon EDN. Indeed, I do not know of any examples where Grumner bases are better than Dixon. Again, given my parameters, I want exact solutions. I'm talking about the ground field being Q or Z, right? I'm not talking about cryptography. It's a different world. Okay, so in this paper, I used an Intel iMac with 16 gigabytes, and I also have access to a couple of servers, one of which has 100 gigabytes. I actually used a lot of that RAM on one of these. And I usually run it on my system from Now, there's nothing, Dixon can be programmed in any system. Great project if anybody wants to do that, or any talented undergraduates. Program it in your favorite system. Oh yeah, I just threw that in. This idea also works on the Macaulay resultant matrix. I proved that a number of years ago. But the Dixon one is much better. Okay, brief explanation. I kind of already have explained it. I'll run through this quickly. You can find papers on this if you look at my website, so I'm not going to talk too much about this. Like I said, we wish to avoid simply computing the determinant of M. M is one of these maximal minors. Okay, we don't want to really say find the determinant. To avoid, so basically what I'm going to do is I start normalizing the matrix. That's a typical Gaussian elimination type algorithm. Just start doing your column and row manipulations. But I make sure that every time I get a rational function, I pull out the denominator from the matrix, right? And every time I could factor, it's like the numerators in a certain row might have a factor. Every time I do, I pull that out. So as time goes on, I pull out these numerators and denominators. Checking often that some denominator might cancel some numerator. Okay. So that's the basic idea. So you go down through until you end up, ideally in the end, you have the numerator list, and of course there won't be any denominators anymore because the original matrix had all polynomials. So better not be any denominators when you're done. So you end up getting a long list, you hope long, of factors whose product would be the determinant if you multiplied them out, if you were so foolish to do so. Subtleties, yeah. There's lots of ways. See, I love this method. I mean, there's so many things you can do. You're in complete control. There's so many ways you can compute determinant. There are pivot strategies. You can run first over Z mod PZ. There's all kinds of things. Furthermore, and this happens often, let's say you start with like a 30 by 30 matrix. So you start doing this, and you get down. And by the time you get to maybe 6 by 6, things are getting ugly. You really don't want to get to, wow, that's ugly. Okay, well, 6 by 6. Gee, compute the determinant with minors. Hey, try that. Right? So I got this enormous flexibility. Try this, try that, do this, do that. Whereas when you do one of these canned Grumner bases, you know what you do. You enter your data, you hit return, and you sit there, and you're powerless. And you go out for lunch or 3-week vacation, as the case may be, hoping that when you get back, it'll be done. Anyway. Okay, so let me talk about these 3 examples. So this first one, some of you have heard me talk about this before. I knew something would go wrong. Let me do the image. This comes from computational chemistry, flexibility of molecules. Let me draw what that image should be. And again, this has a long history, which I don't have time to go into. But imagine you have 4 rods in the plane. These are rigid rods, and they're joined at flexible joints. So this is a quadrilateral, so of course you can move this in and out to be flexible. Okay. Now suppose you added a rod here, and then you put a rod like that. So these, again, these joints are joints. Okay. So you added this stuff. Now that's still flexible, intuitively. As you're moving that up and down, opening it up and down. Okay. And now the kicker is now let's add one more. See, that's not flexible anymore. This is now rigid. Okay. It's generically rigid. Do I have that there? Was generically rigid there? Well, anyway, this is generically rigid. In other words, if you just assign the lengths more or less at random and make some reasonable looking figure, it'd be rigid now. Okay. Well, the whole point is, how can this be flexible? In spite of the fact that it's generically rigid, is there some way to make it flexible? This question was first asked back around 1896 by Frenchman Ricard. This may seem like an arbitrary thing to look at, but believe me, this is not arbitrary. This ties in with certain chemical compounds, even though it's not obvious at first. So how could this possibly be flexible? Well, I'll give you one way which I think is intuitively clear. If they're all parallelograms. Right, so imagine, so that's a parallelogram, and that's a parallelogram. Okay, now think about that. If they're all parallelograms, that's going to be flexible.
Is that the only case?
No. No. Like I say, this is a big, long story. He and I just published a paper. It'll be coming out in a month or two. But there are some, Ricard knew about a couple other ways. So his nickname is Vigeli. Professor Koutsias and I, in fact, you worked on this briefly. But anyway, what we wanted to do was automate this, because this is part of computational chemistry. You want to be able to detect, like imagine a molecular structure, is it flexible enough? Okay, so we wanted to write a program that could do all this. Okay, so like I say, there's a paper on my website if you're really interested in this. It's a great topic. What it boils down to is it's a resultant computation. The parameters are the lengths of the sine. The variables are the sine or cosine of these 3 angles down here. you can write a system of polynomial equations that define this structure. You can compute the resultant. The resultant has something like 191,000 terms. It's a little bit more than that. It's a little bit more than 191,000 terms. It's of degree 7 in the cosine. So you have the cosine, only one angle is left. You have the cosine of one of the angles. And then you have, I think there are 11 sides. You have 11 parameters for the sides. Okay. So first you compute this resultant. Then I developed a program which will analyze the resultant and figure out how you can get flexibility. Okay. And there's a long story there, but let's see now. I can play this movie. How do I
Just
go back to
Or
the...
press Control Alt.
Where's the movie? Yeah, that's it. Oh, it's already started. Okay. The algebra and the program told me how to make this. I made this model out of cardboard about a year ago. Thumb fast. This is a new case that was not known to Burckhardt. It's what I call an exotic structure. In fact, there are at least 2 new exotic structures that were discovered by this program. Okay, so you get the idea. Pardon me?
There was like a 2 sticks that crossed each other. Where is that in your picture?
That's okay. Oh, some of these are down here. Some of the sides are negative, so they're down below the axis here. You want to see it again, or? Okay, well, we can talk later, okay? Now I got to go back. Do I just click
I'll
on
take the reader.
Yeah, I don't do Windows. All right.
Full screen mode.
only click.
Control plus.
That's good. Okay, so that's my first example. Like I said, you'll find a paper on my website describing this. Okay, now, second type of application, pose estimation. I've got an image for that too, but maybe I'll just draw it. First of all, there's a classic problem in pose estimation is you've got this object and you have a camera or like your eye and you're looking at this thing. Okay. So a classic situation is you've got 4 known points. So you could think of this as a, well, quadrilateral again, but think of it as a solid object, right? Flat. And let's say your camera or your eye is up here, right? So the object is known. That means in the beginning, you know these various sides. You know all 4 sides. You know the 2 diagonals. Okay, now you're viewing it from some point up here, let's say. So when you view it, that means you have these lines of sight. And so you know these angles. You can tell what the angle is, right? So then you can easily write down, I think, 6 equations based on the law of cosines. So 6 equations, law of the point is what do you want to know? You want to know these sides, right? These lengths, x1, x2, x3, x4. You want to find these 4 distances. Deduce the distances given the angles that you're observing. Okay? Now this is a classic problem. This, the equations are really pretty simple. It's just law of cosines. But you can do, I believe there's 6 you can do, right? 4 choose 2. Right? Okay, anyway, so I think there's 6 equations you can write down. And they're pretty simple, and this is like 30 years ago. This is what's considered an important problem. And it's quite easy to solve, certainly by today's standards. It's quite easy to solve. Okay, so for whatever reason, about 2 months ago, maybe because of my flexibility work, I got the idea, well, now, wait a minute. So you've got this object down here, right? What if the object is flexible, right? What if it's not a solid piece of wood or something with 4 points? What if it's 4 rods? If it's 4 rods, then it's flexible, and that means you don't have the diagonals. You don't know the diagonals. The only thing you know are the 4 lengths, right? The A, B, C, D, you know. You only know the 4 lengths. Now, how does that impact the problem? It impacts it a lot. Because the way this was solved 30 years ago, remember I said there's 6 equations? The key is to pick 4 of them and make sure you use the ones that involve the diagonals. As long as you use the ones that involve the diagonals, you have the system of equations is quite easy to solve by virtually any method. But now you can't use the diagonals. You have to use the 4 that go around. And believe it or not, that's enormously harder to solve. That system of equations is much harder. Let's see. So that's what I did. It was about 2 months ago. I tried Maple and Magma. They both failed. Now, I am not an expert on Magma or Maple. In Maple, I've been using Fougère's FGB. Anybody, you all know about Fougère? No? Yes. Well, Fougère is a French mathematician who's developed some really great Grosvenor-Basies algorithms over the last 10, 15 years. And they are embedded in the latest versions of Maple. It's called, if you get the right Maple, it's called FGB is what you invoke. In fact, for a while there was a problem with it. It didn't seem to ever work. About a year ago, he fixed the problem. And now it really is nice. It does work on these things often. So anyway, I tried both Maple and Magma on this system, the cyclic outer system, trying to find the resultant. So what I do is I want the resultant that involves, let's just say, x1 and the 4 angles. I want that polynomial. Then I can, look at the data, get my cosines and fill it in and blah, blah, blah. Okay. So yeah, I killed Magma after 40 hours, and FGB gave up after 5 hours. I forget how much RAM Magma used. Anyway, I finally killed it. Yeah, Dixon EDF finishes in 32 seconds, uses 275 meg of RAM to compute the resultants. Okay, so that's that pose problem. Now this one, this is a more sophisticated pose problem. So let me draw some pictures. The idea here is, suppose you have a known 3-dimensional object. Maybe, as a first case, maybe it's just an ellipsoid. So you have a known ellipsoid, you have an equation for it. Okay. And then what's the deal? So it's sitting here in 3 space. Okay, suppose it's rotated. So you can imagine rotating around each of the 3 axes, and then it moves, and then it's moved off. So after it rotates and moves, it's off somewhere else, right? Okay, so now what do you do? Well, now you have a camera again, so these camera things. Imagine you are at the origin, let's say the origin. So you're looking at this thing, what can you do? You can snap a photo of it. When you snap the photo of it, you will get a 2-dimensional image, right? And since it's an ellipsoid, it won't be too exotic. So you have this 2-dimensional thing, and the problem now is, given that, figure out what were the 3 angles and what were the translations that brought it into this position. So from that image, determine the angles and the translations. Okay, so there's my sketch. Right. Now, the first step is to eliminate the z. So here's a test case. Here's an ellipsoid, has 4 terms. Then you apply the simple, I'm doing this rather straightforward. I'm just doing the obvious rotation matrices. So you rotate and translate, and the polynomial ends up being with about 260 terms. Okay, now what? Now you want to eliminate z. Now it turns out there's a fairly easy way to do that. If you imagine viewing from the origin and you know, cutting the tangent, right? The view from the origin has kind of a tangent intersection. It turns out there's really a rather elementary way to figure out what that equation is. At least you get an equation it has to satisfy. Has some partial derivatives in it. So you get 2 equations. You get the original XYZ equation, and you get this second equation involving x, y, and z from partial derivatives. And you eliminate z. Okay, so that's the first step. So by eliminating z, it's like we're now looking at the 2-dimensional image involving only x and y. After you eliminate z on this example, the resultant has 1,414 terms. Okay, now what? I have to do, okay, it's a very difficult problem. I'm going to assume that the object has a distinguished point. So there's some distinguished point that I can still see. So what I'm going to do is, because I have my eye here at the origin, I'm thinking of it as a camera, I'm going to move until I'm looking right at that point. By looking right at that point, I can effectively get rid of 2 of the parameters. V1 and V2 are 2 of the displacements. I can get rid of those by assuming I'm going to rotate to that point. That leaves me with about 400 terms. There are now 4 variables. T1, T2, and T3 are in fact the tangents of the angles. V3 is the other shift. And it's degree 4 in each of the variables. Okay, now what do you do? Now, ideally what you would want to do, you'd want to proceed abstractly. You would want to replace the data, everybody is an XY. You want to plug in x1, y1, x2, y2. In other words, you're saying, okay, suppose this point right here is x1, y1. Suppose this one is x2, y2, right? Here's x3, y2. Here's x4, y2. So let's plug in 4 points into the equation. That now gives me 4 equations. So like, the resultant, by plugging in the x1, y1, etc., now I have 4 equations. Okay, so from 4 equations, I can eliminate, let's say, T2, T3, and V3. That'll be the resultant, and we'll finally have 1 equation left in T1, say that's Y1, and these abstract x1, y1. So that later, I can now actually plug in numbers, maybe, solve the equation, and I'll know one of the angles. So it's like a 2-step process. Okay, so that actually worked. Yeah, I didn't write down the details of that. I thought I did. Okay, it didn't take too long. Wasn't too bad. However, FGB and Magma both failed on it again. Okay, now, this is nice, but that's an awfully simple shape. We want to do this for more general shapes. According to my colleague, the holy grail would be to do this for an arbitrary degree 4 shape. Not degree 2. Apparently, if you have degree 4, you can generate lots of interesting stuff. Okay, that's really hard. I can't do that. That's really hard. Well, how about degree 3? Okay, so I generated a certain heart-shaped cubic. So you start from the beginning with a cubic thing. The resultant now has 6,278 terms. Instead of being of degree 4, the degree is now 12. In these variables. That's a big mess. Furthermore, I couldn't do this. I had to actually plug in, I made up some data. I made it up, I admit. I plugged in 4 points to assume that it was on the shape. So now what I've got is, imagine this, you got 4 equations. each of degree 12 in each of the variables, but now there are no more parameters. Okay. So I gave it to EDF, it worked, it took 38 hours, it used about 5 gig of RAM. So in the end, you have just one polynomial, and I guess it's like T3. Okay, well, anyway, whichever T you want, I have a polynomial of degree 480 in that, and numerical coefficients. Okay, that worked. Right, and so to make this go to the next level, to get degree 4, something new is going to have to be brought in here. I tried, instead of the typical Euler angles of rotation, I tried using quaternions, but that didn't seem to do any good. So if anybody has any ideas what to do, let me know. Okay, third example, analysis of point clouds. I should have copied over the other paper. There's another PDF I should have copied over.
Oh, we can do it.
Do you want to stop and do that, or I can just?
So we can switch it to your computer too.
I really should have done it. Well, just a minute. Let me introduce what this is about. What's going on now is this is called laser scanning. So the idea is you take this, there's this thing called a laser scanner, and you point it at a scene, like you go outside and point it at a scene, and it will produce thousands of individual points. It's like it scans and gives you a giant data array of thousands of points. I'll have to show you the image from my colleague's paper. But just imagine that there's a sloping hillside, and there are like trees on this hillside, or bushes, right? So you get, I think it's like 30,000 points scattered all over the place. Right. Some of them come from the trees and bushes, some of them come from the hillside. Okay. What you want to do is figure out the equation of the sloping hillside. So the idea is that the points that correspond to this, we are considering inliers, and these points we are considering outliers, that we really aren't too interested in those. What we want to do is end up getting the equation of the plane. So how do we separate these two, the inliers and the outliers? The answer is, now this again is a big subject evidently. The subject I know very little about. I really am just a guide into this via these people I know. So there are various other methods to do this. But the method we're proposing is you're going to separate the two by expectation maximization by a Gaussian distribution. So let me try to explain what I mean by that. So what's going on here is the equation of the plane looks like this. Z is alpha x beta y plus gamma. We want to determine the parameters alpha, beta, and gamma. Okay. And what we're going to do is use, let's see if I have this on the next. Yeah, I'm afraid I really do need that other paper. Should we take a break a minute? Yeah, let me get it. I should forgot. It's this one. The idea is that given that these points are distributed according to the normal Gaussian distribution, you want to find what alpha, beta, and gamma are to minimize the error. It'll make more sense if I bring up this paper. Algebraic, that's it. This gives you an idea of what we're talking about. Here's this laser scanning thing on a hillside. So here is the point cloud you get. So the idea is that we know we expect to find a plane in there. And so what you do is you take every single point and you get an expression, pretty elementary, of the distance from a point to this plane. Just write down, in other words, you have your ith data point, xi, yi, zi. Figure out the distance from this point to this plane. Just like a multivariate calculus type problem. Okay, so that thing is what we're going to now apply. We're going to assume we have a Gaussian distribution, a normal distribution of that. And what we're going to try to do is minimize the error. It's a two-step process. So here are some test cases. See, this is the second equation. Okay, so this thing is the normal function. This is for each point x sub I. So if each one of those is according to this normal distribution. You have many of them, you have n of them. So you would multiply that all together. If you take the log, you end up with the sum of all those things. And then what you want to do is minimize the sum of all those things. Find the alpha, beta, and gamma that minimizes the sum. Okay. So it's a two-step. So in the first step, we have no idea what's an inlier and an outlier. We just do one Gaussian distribution, not two. You do one Gaussian distribution, and you get an initial estimate of alpha, beta, and gamma. Okay. When we go back to the other paper, I'll show you the equations for that. It ends up being a polynomial equation. You got a polynomial equation, you have a system. You have, well, how do you do it? You take some partial derivatives. So each partial derivative gives you a polynomial equation. You have a system of polynomial equations involving a whole bunch of parameters, which ends up being various combinations of these data points. Their sums, their products, the products of one with the other, and blah, blah. You get like 12, I think, of these parameters. So that's the first system of equations. That gives you your first alpha, beta, gamma. Then what? Now you have a more sophisticated system of equations based on the fact that there are going to be two. One set has its mean and standard deviation. Another set has its mean and standard deviation. And now we're going to use a double Gaussian distribution. Once again, get a better alpha, beta, gamma. So what goes on? You end up with a loop. You end up saying, I have an estimate of alpha, beta, gamma, and an estimate of what's in and what's out. Using that, I get a new estimate of alpha, beta, gamma. Feed the new estimate of alpha, beta, gamma will give you a slightly different inlier and outlier set. So you go around until it converges. That's the basic idea of this algorithm. Okay, how do I go back now? I'm afraid I'm going to need you again.
Press escape.
Escape?
And now you can.
Is this one right here?
Yeah.
Okay, good.
Full screen, go to the
Control
window.
L.
Where
Or
is
view.
here?
View probably.
Minimize.
No.
Next to
View.
window.
If you go to view.
Control L.
Control L.
Control
L.
L.
There you
And Control plus a couple
Control plus.
And one.
Okay, so here are the three equations that come from the first step, where I just am assuming it's one big data set. This is the first equation, this is the second, the third one's very simple. So you want to solve that system of equations. The Dixon ETF will find the resultant either alpha or beta in about 1.5 seconds. FGB failed, gave up after 66 minutes. Magma gave up after 440 minutes. Typical. Okay, but anyway, so now I have I have these resultants for alpha and beta. The one for gamma is easy after you know alpha and beta. Now the real problem, like I said, use the result of step 1 to feed it to a double system, inlier and outlier, each with its mean and standard deviation. Okay, that system of equations is like this. Here's the first one. You have your alpha, beta, gamma's in here. So there's a new variable called delta. It's an artifice. And you have now 24 parameters. So here's the second equation. Here's the third equation. Here's the fourth equation. Now that's enormous. I couldn't solve that. But then I noticed that a lot of linear substitutions can be made. For instance, if you replace G2 with G2 plus G1 sigma 2, there will be no more G1 after that. Interesting bunch of equations. In fact, you can do that about 8 times. If you do that, the reduced system is enormously smaller. There's the first equation. The second equation, the second equation ends here. Oh, up there. There's the third equation. And only 15 parameters left. Now that's still a toughie. I gave that to Dixon EDF. It took 3.5 hours and 28 gig of RAM. And it produced an answer of 21 million terms. This is the largest problem I've ever successfully solved, 21 million terms. However, there were a lot of contents. You can factor out the contents and you get it down to only 759,000 terms. So that's the result. At 759,000 terms, the degree is 14. So now, you run this loop I talked about. So if you have your data set, the real data set has like 30,000 points in it. So from all those points, you compute these 15 parameters, plug it into the resultant for alpha, the angle alpha. This is what you get. So this is what we're talking about after plugging in the numerical values. The one for beta is similar. So using that, you can go through the loop and get your new alpha, beta, gamma at each step. And it converges fairly rapidly. It's like 5 or 6 times through the loop, you're seeing convergence of alpha, beta, and gamma. Okay, so I see I'm ending on time. Okay, so in conclusion, I find great success in using this method in polynomial systems in many important applications. Grosvenor bases, as far as I know, have failed on all of these. Well, almost always. So here's my open challenge. Some of you may know more about magma than I do. So fine, use magma and solve one of these. Use maple and solve one of these. Okay, this is my challenge. Okay, that's it.
Questions?
One question. You said in the beginning that you will compute just single root. That you promised to compute the single root with this approach, but it seems that in the example you needed not just single root.
Oh, you mean I need alpha and beta and gamma?
Mm-hmm.
Right, well, you get a resultant for each. You do the resultant for alpha, you do the resultant for beta in exactly the same way.
So you did it in parallel, maybe?
Exactly. You can do it in parallel.
Other questions?
You want to see the movie again? Okay.
I'm wondering where the cross came from.
The cross, it's just, oh, I erased the picture of a,
There was no cross in the picture, though.
well, that's because it goes down
Were
underneath.
jointed.
I'll show you the movie.
Yeah?
Sure,
Actually-
or I can show you here.
Actually, before that, continuation of my question, how frequently in applications do you need single root of polynomial system?
Single root?
Yeah, because it's a different problem technically to compute just a single root.
You mean for, you have a bunch of variables and you want the
Yeah.
resultant for
Yeah.
one variable?
Yeah.
Right.
It's,
Well, like I said, if you want all of them, then you can do, oh, I see what you're saying. You can do all of them,
Yeah,
but
that's-
now you have to figure out what the solution is.
yeah.
If you really want the total solution, you'll have to write a loop numerically or something to figure out, you might have 4 values for alpha and 5 values for beta. You got to try them all.
Yeah,
Yeah, that's part of it.
More work actually.
It's a little bit more work,
Yeah. So,
but it's not much.
But not much.
It's really not much. Yeah, for instance, I didn't have time to talk about it. In this last example, or that equation right there of degree 14, it always has either 8 or 6 real roots. So you've got to pair that like the 6 alphas with the 6 betas. And you plug into the original system and see what the root is.
But in principle, sometimes you don't need all your happy with single one.
Right. Going back to the example.
Real applications, real life applications. Sometimes you need just single.
That's right. That's right.
Okay, excuse me.
No, fine.
You plan to show something?
The movie?
I'll show you the movie if there's no other questions. All right, come watch the movie.
So
Well,
here
either
on the
way.
screen.
Oh, either way. So which part were you? Oh, okay, it's got it.
The 2 sticks that are crossing each other, right?
Yeah, that's because some of the lengths are negative. You're below the axis. That's what's going on.
I think what it means is that you have a nail in the middle of a rod.
Yeah, because
So that's also allowed problem.
Not following.
So in the example, you have a blackboard.
Right, well, you start with, take this length and nail it down. This one's nailed to the ground.
So in
Then
the
the other guys can all
like
move.
your algorithm is sort of a more general type. So even there are other nails even there's one extra nail in a node, then you can still
It's
solve
not
it.
the nail, it's that one of the points.
I'm not sure I'm following. I mean,
There's like a corner, and then there's a point on one of these lines, and then that
Right.
point is moved all the way past the corner, so that it has to extend.
right, imagine you simply had a quadrilateral.
Yeah.
If you wanted to, you could drag this down here.
Yeah.
See, it could be dragged below, and this could turn
Oh, so
into
doing-
this could turn
yeah,
into
okay.
that shape.
There is over. Okay.
That's what's going on.
Other questions? Thank you very much. Yeah.